Find a really dark spot on Earth, far from city lights, and look up. You will see thousands of stars scattered across the sky. If you trace the line from the distinctive W shape of the Cassiopeia constellation, it points right toward a faint, slightly elongated pale puff of smoke. That is the Andromeda Galaxy. Under optimal conditions, this tiny smudge is the absolute furthest object your eyes can perceive without the help of a telescope. The light hitting your pupil has been traveling uninterrupted through the vacuum of space for nearly 2.5 million years. For over a millennium, this light fell on human eyes as an unresolved puzzle, a signature of a reality we were not yet equipped to measure. For most of human history, astronomers believed the Milky Way constituted the entire universe. Every star, every planet, and every cloud of gas existed within our own galactic borders. As far back as the year 905, Persian stargazers mapped this specific object simply as a little cloud. Looking at early telescopic observations, it is easy to see why. The fuzzy, unresolved shape looked exactly like a local pocket of gas. By the 1920s, this ambiguity sparked a fierce debate among scientists. One camp argued these spiral clouds were local nebulae trapped within the Milky Way. The opposing side proposed they were entirely separate island universes floating millions of light-years away in the void. Settling this argument meant deciding whether the cosmos ended right outside our solar neighborhood or extended into distances we couldn't even comprehend. Resolving the nature of that little cloud required the precision of the early 20th century observatories. It also required the work of American astronomer Henrietta Leavitt, who discovered a mathematical link between the pulsing cycle of specific stars, called Cepheid variables, and their underlying brightness. This became known as the period luminosity relationship. Think of two identical parked cars. Their headlights output the same amount of light. As one drives away, its headlights appear dimmer. Knowing the bulb's true brightness allows you to calculate its exact distance simply by measuring how faint that light appears. Edwin Hubble took Leavitt's headlight rule and applied it directly to a Cepheid variable star he found pulsing inside the Andromeda smudge. His calculations returned a distance of about 1 million light-years. That single number proved that Andromeda was located entirely outside the Milky Way. Our galaxy was suddenly just one of many floating in a massive, crowded cosmos. Today, we know Andromeda is a massive, barred spiral galaxy holding roughly 1 trillion solar masses, with a diameter stretching 152,000 light-years. It is significantly larger than our own Milky Way. It grew to this size through a process called galactic cannibalism. Over its 10 billion-year lifespan, Andromeda's intense gravity has pulled in and swallowed up smaller dwarf galaxies at least twice. Deep inside the galaxy's center, NASA's Fermi telescope has detected a highly concentrated excess of gamma-ray signals. Astrophysicists suspect these energy bursts could be coming from a dense cluster of pulsars, or possibly from the accumulation of dark matter. Andromeda behaves as an active force within our local cluster, its 150,000 light-year span carved out through billions of years of gravitational acquisition and destruction. While Edwin Hubble discovered that most of the universe is expanding away from us, our local group of galaxies behaves differently. Andromeda is heading directly toward the Milky Way. It is closing the gap between us at a speed of 68 miles every single second. In roughly 4.5 billion years, these two colossal galaxies will physically collide, eventually merging into a single, massive supergalaxy scientists currently call Milkdromeda. You might expect a violent crash, but the physics of a galactic merger are counterintuitive. The stars inside a galaxy are spaced so far apart, comparable to 2 grains of sand separated by the entire length of a football field, that the chance of any two individual stars actually hitting each other is essentially zero. Rather than an apocalyptic destruction of planetary systems, the two massive bodies will pass through each other in an incredibly slow cosmic dance, gravitationally reshaping the entire architecture of our local space. If you were hoping human descendants might watch the spectacular light show from backyard telescopes, the timeline doesn't work in our favor. Long before the two galaxies actually merge, our own sun's luminosity will increase by nearly 40%. This runaway greenhouse effect will boil the oceans and extinguish all terrestrial life on Earth. This single object provided the measurement that broke open our understanding of the universe, revealing a landscape populated by billions of other galaxies. The light from this distant neighbor revealed the scale of the universe, yet it also marks the path of our eventual collision, the approach of a force that will eventually consume our galactic home.